Hi, everybody. So in this video, we're going to talk about how carbon dioxide moves through the blood. Now, we're going to move carbon dioxide. So remember, we're bringing CO2-rich blood to the lungs so that we can get rid of that CO2, right? And that we make CO2 in our tissues as a byproduct of undergoing metabolism. So our bodies need energy, so we have to burn molecules for energy. When we burn those molecules for energy, we produce CO2 as a byproduct. So our tissues are constantly going to be secreting these. So how do we move CO2 around then? It's not like oxygen where we can just stick all of it onto a hemoglobin and call it good. That's because oxygen doesn't dissolve really, really well in water. So we have to kind of grab a hold of it. CO2 is a little different. CO2 also has a low solubility in water. So we're not going to find a bunch of it just found in the blood plasma. It's just dissolved as CO2 necessarily. Okay. Some of it will be because there is some solubility. So we're going to actually have around 7% of the CO2 that we make. It's just going to be found dissolved in the blood. Okay. Or dissolved in the blood plasma. Okay. Now, 23% of that, of the CO2 is going to be found bound to hemoglobin. So oxygen releases, or like hemoglobin releases its oxygen molecules, and then those CO2s will come in there and just like grab onto exposed amine groups on those hemoglobins and like grab onto those. Okay. And that's going to cause a little bit of a conformation change in the protein once again. Okay. So 30% of the CO2 moving through our blood is going to be found as CO2. 23% of the CO2 is found bound to hemoglobin. 7% is found dissolved in the blood plasma. That's only 30% total though. So where is the other 70? Well, the other 70 is found as what we call bicarbonate. Okay, so bicarbonate is H2CO3. Okay, so bicarbonate is basically a soluble form of CO2. So what happens is you breathe in, or you breathe out, your cells, your blood goes down, that CO2 leaves your tissues and it enters the bloodstream. And once it hits your red blood cells, we actually have a protein in there, an enzyme called carbonic anhydrase. So anhydrase. So we are basically dealing with some kind of water functions here. Okay. What we're going to do though is we're going to take that CO2, we're going to stick it to water while breaking that water apart. So we're going to produce bicarbonate. So that's our H2CO3. So we're adding two H's and we're adding the oxygen, thus water, right? So we're adding those to that CO2. So now we have this H2CO3 molecule. Now H2CO3 is soluble. However, because it's soluble and because we have those H's a little bit separate from the CO3, one thing that'll often happen, or also sometimes happen, is that those two things will dissociate from one another. Okay, so if we just put those out into the blood plasma, which is what we do, sometimes they will dissociate. Not all the times, but sometimes. And when that happens, we're actually going to lower the pH of the blood because of that free hydrogen molecule, or that free hydrogen ion. Well, H plus, well, that is an acid by definition, right? So excess CO2, so say you aren't breathing fast enough, or you kind of cover your mouth and you hold your breath for a little while. Well, at that point, CO2 is going to build up in your blood. Well, when that CO2 builds up, we're going to have more hydrogen ions, and thus we're going to lower our blood pH. We're going to make our blood more acidic or cause acidosis. Okay, that's what happens when we say, or when we don't breathe enough, or what we might call hypoventilation. Okay, now in order to help this, in order to help the bicarbonate get out of the cells, what we're going to have is we're going to see what we call a chloride shift. This basically means that we're going to have these two cars basically pass each other going different directions on the highway. So chlorine will come into the cell. As chlorine comes in, the bicarbonate is going to leave. So chlorine comes in, bicarbonate leaves. Now, this process is reversed. So we're going to see chlorine leave the cells and enter back into the blood, or back into the plasma. And we're going to see the bicarbonate go back into the blood cells whenever we enter the pulmonary capillaries. So we can kind of reverse these processes. So we can basically regenerate CO2 as a gas from the bicarbonate ion that was in the blood plasma. So let's look at this here. All right. So we're just going to kind of walk through this figure. This is figure 23.31 for those kind of keeping track. So CO2 diffuses into the erythrocyte. Cool, that makes sense. We know that 23% of the CO2 is going to bind itself to hemoglobin. The other 7% will stay just in the blood plasma, but the other 70% is now going to get exposed to carbonic anhydrase. This is where we're going to generate that bicarbonate ion. Now, remember that bicarbonate ion can dissociate into bicarbonate and a hydrogen ion, okay? So carbonic acid, H2CO3, so carbonic acid because it dissociates into that hydrogen ion, right? So this is your equation here. It doesn't always do this, but it can. So it's considered a weak acid, but it is still acidic. So if you have a buildup of this carbonic acid, that means you have a buildup of CO2 in the blood. Well, why would you do that? Well, because you're not breathing enough, or something is stopping your ability to breathe enough, or you're undergoing a lot more metabolism. So if you can think of a circumstance where you might be undergoing additional metabolism, like say exercise, right? So that exercise that you're doing is going to increase the amount of CO2 that's getting pumped into the blood, at which point you're going to have a raised CO2 concentration or a raised carbonic acid and thus bicarbonate concentration, which is going to lower the pH of the blood and make your blood more acidic, okay? Now, to get that bicarbonate that we just made out of the blood, what we're going to do is we are going to have chlorine move in. So chlorine ion, so the chloride part of salt, is going to move into the red blood cells, and then the bicarbonate ion is going to leave, okay? So chloride ion in, bicarbonate leaves. So this is what we call that chloride shift, okay? Now, once we get back into the pulmonary capillaries, we're basically going to see this process reverse. The first thing that needs to happen is we need to get bicarbonate back into the red blood cells so that we can take that hydrogen ion, slap them back together, turn it back into carbonic acid, which then we can turn back into CO2. Okay, so first thing is chloride moves out and bicarbonate moves back into the erythrocyte. The hydrogen ion here finds its bicarbonate. And then now we have our carbonic anhydrase basically putting them back together. So the same enzyme that we use to tear them apart puts them back together. Then we now have our CO2 and water. CO2 can then diffuse across and back into the alveolus so we can expel it. So this is actually one of the ways that we can actually regulate our blood pH through the process of breathing. So like I said, if you are, say, running or something like that, where you have increased metabolic activity, that increased metabolic activity is going to lead to increased amounts of CO2. So increased CO2, which means we're going to have increased levels of this bicarbonate, which means we're going to make our blood more acidic. Another way that we can make our blood more acidic is simply not breathing fast enough. So you hold your breath. Well, if you hold your breath for a little while, you'll notice that when you start breathing in, you're going to breathe a little bit faster and you're going to breathe a little bit deeper. You're going to do that so that you can exhale or so that you can inhale additional oxygen because you made your blood really, really oxygen poor. But you're also going to be breathing in some CO2 in the process, and you're trying to basically kind of concentrate that. This is why, so say you have someone then that is hyperventilating. Okay, so someone that is hyperventilating, they're breathing too fast. They're getting a bunch of oxygen in, they're getting a bunch of CO2 out, but they're breathing really, really, really fast. Well, what this will cause is this is going to cause them to actually have a lack of CO2 in the blood. So their blood will actually get more basic. So when someone is hyperventilating, they're breathing too fast, their blood will actually get more basic because they're getting rid of, honestly, too much CO2. So what do we do when someone is hyperventilating? We have them breathe into a bag. Why do we have them breathe into a bag? So that they will inhale additional CO2. And by inhaling additional CO2, they can actually bring the pH of their blood back down to that 7.4. So someone that is hyperventilating, you can actually watch their blood pH sometimes go into like 7.5, 7.55 or something like that. We want to bring that number back down to that 7.4. We do that by having them breathe into a bag so that we can make that blood a little bit more acidic. So this is actually one of the ways that we can regulate blood pH, is by regulating these levels of bicarbonate ion in the blood and how we move it around. So if you have any questions about blood pH or respiration or anything related to this chapter or any other, please just let me know. All right, thanks. Bye.